Hello guys, welcome back. Myself Assistant Professor Gaurang Prajapati from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. So, in the previous two videos, we have discussed the topic of the plastic design method, okay, of the subject DSS. Now, in the first video, we have discussed the theoretical portion as well as safe factors example. In the second video, we have covered the derivation of the equation using the static and kinematic method. So now in this third video we are going to analyze some of the examples using the kinematic method. Okay, so see, let's start the example. Now the data stands for example number 1. Calculate the plastic moment capacity required for the continuous beam with the collapse load shown in figure. It has been asked in May 2018 in 7 marks. Now, the beam is given there in the data. See, it is a continuous beam. We can say ABC. Span AB is acted upon by 60 kN eccentric load, 4 meter from A, 1 meter from B. While in the portion BC, it is acted upon by a central point load, 3 meter, 3 meter. So, first of all, let's talk about the plastic hinge. Plastic hinge will be formed obviously at the point where moment will be produces. So, it will produces at A because of fixed support, then at B, that is because of intermediate support, and the location of the point load we can say like this. Okay. So, first of all, let's take the beam separately as we were doing in the previous example also. So, first, just draw the beam mechanism. See, let's consider the span AB. So we need to draw like this. Okay. Now, in this one we can see that the load is not central point load, it is a eccentric load. So 4 meter at the left hand side, 1 meter at the right hand side. Let me highlight the figure properly. Say this one like this. Now this one is 4 meter, this one is 1 meter. So first of all we need to derive the relation between the theta. In this one theta will not be equal as it is not the central point like the previous other cases. So in this one theta relation will be 4 into theta equals to 1 into theta 1 like that. So 4 into theta equals to 1 into theta 1. So ultimately we will get the relation theta 1 equals to 4 times theta. And talking about deflection, we can derive deflection in both terms, either in terms of theta or we can say theta 1. Say let's consider the right hand side triangle. So tan theta equals to these dimensions, that is deflection, divided by this dimension 4. So tan theta equals to, we can say, delta by 4. So delta equals to 4 into tan theta. Say tan is very small, so deflection equals to 4 theta, that is this one. Okay, so we got the value of the deflection as well as relation between the theta 1 and theta. So now let's solve the sum. Say let's start first external work done. External work done means load into its deflection, that is this one. Okay, so 60 into, we can say, 4 theta. So 60 into 4 theta, so answer is 240 into theta. Now let's talk about the internal work done. So talking about internal work done, over here at A, fixed support, so moment will be produces. At the center, moment will always produces, and at B, because of intermediate support, once again moment will be produces. So we need to consider all 3 points, A, D and B, that is this one. Okay, so first of all, this MP into theta, that stands for this moment. Then this MP into theta plus theta 1, that stands for this one. And this MP into theta 1, that is this one. Okay, so now put theta 1 equals to 4 theta. So theta 1 is at 2 places over here. So 4 theta, theta 1, that is 4 theta. So by simplifying this one, MP into theta, MP into theta plus 4 theta, and MP into 4 theta. So by simplification we will get 10 MP into theta, that is internal work done. This one is external work done. So let's solve these two, say equal these two terms. So internal work done equals to external work done. Internal is 10 MP into theta, that is this one, and external is 240 into theta, that is this one. So theta will be cancelled and MP will be 240 by 10, so that is 24 kilonewton into meter. So we got the plastic moment of the span AB. Okay, so what we have done, we have separately solved the first span, that is AB. Now let's solve the another beam, say another span, that is BC. Now B will act as a as it is intermediate support, it is a fixed support, so it will act as a prop cantilever beam with central point load like this one. Okay, so let's solve this one. Say span BC. Now so plastic hinges will be produced at B, intermediate support, then at the center moment will always be produced, say give it as a notation E, and at C moment will never be produced as it is a simple support at the end of the span. Okay, or we can say at the end of the beam. So let's talk about beam mechanism. We have solved this kind of sums before also. Say as it is a central point load, so both theta will be equal. Okay, and central deflection will be there. So let's derive the first of all say relation between theta. This 3 into theta equals to this 3 into theta. So obviously both theta will be equal. There is no issue with that one. Now let's derive the value of deflection. Let's consider any of the triangle, left or right hand side. Say we need to derive the value of deflection, that is this one. This one is deflection while this one is 3 meter. So tan theta equals to deflection by 3, so deflection equals to 3 into tan theta. Say theta is very small, so deflection is tan theta. Okay, so that's the value of deflection. So now talking about external work, so load into deflection. Load is 40, deflection is 3 theta, so I got the answer, that is 120 into theta. That is external work done. Talking about internal work done, so first of all this MP into theta will be calculated. So this MP into theta, then this MP into theta plus theta, that means twice theta will be calculated. Over here no moment is there, so no moment is considered. So ultimately simplifying this one, I will get 3 MP into theta. So ultimately 3 MP into theta equals to 120 theta. Let's equal these two terms. 120 into theta equals to 3 MP theta. Theta will be cancelled, so MP equals to 120 by 3, that means 40 kilonewton into meter. So finally we got two moments. Say span AB's moment is 24 kilonewton into meter, while span BC's moment is 40 kilonewton into meter. So finally plastic moment capacity will be the larger of the two values, that means maximum value. So obviously answer is, that is 40 kilonewton into meter. So that's the first case. We have solved this beam using the kinematic method. Now let's solve another sum. See this one, example number 2. Say calculate the plastic moment capacity required for the continuous beam with working load shown in figure below. Take load factor equals to 1.5. 7 marks, November 2017. Okay, now as in the data they have given us the loads are working load and load factor is given. So first of all we need to convert it into the collapse load. Say load factor is 1.5, so collapse load equals to, say first of all this 40 point load, so 1.5 into 40, answer is 60. Then this 20 kilonewton per meter, so collapse UDL equals to 1.5 into 20, so answer is 30 kilonewton per meter, that is this one. Okay, so we have converted this load into the collapse load. Now let's solve the beam separately as we have done in the previous example. Let's solve the span AB. Say central point load is there. Now we can see there is a variation in the moment. Say in the span AB moment is MP, while in the span BC moment is twice MP. So we need to consider this one also. Okay, so first of all let's talk about the span AB. Say let's zoom out the figure. So span AB, that is this one. Okay, now because of the central point load, deflection will be at the center. So as it is a central point load, so both theta will be equal. So theta equals to theta, means if we are taking 2 theta, then theta 1 equals to theta 2, but we will take theta as a constant as it is a central point load. Okay, so over here at A, corner simple support is there, so moment is never going to produce over here. Now at center, moment will always be produces, and at point B, as it is a intermediate support, so moment will be produced. So at 2 points moment will be produced, at center and at B. Okay, let's talk about the deflection. Say we need to calculate deflection, this one. Say this one is deflection, so we can say tan theta equals to deflection divided by this span, that is 2 meter. So deflection equals to 2 into tan theta, so tan is very small, so deflection equals to 2 theta. Okay, so let's see the explanation. So first of all, using the kinematic method, external work done equals to this load 60 into this deflection. So 60 into 2 theta, that is 120 into theta. That is external work done. Now talking about the internal work done. So first of all, this MP will be considered, say MP into 2 theta plus this MP will be considered, that is MP into theta. So ultimately 3 MP into theta. Now let's equal both terms, external as well as internal. External, that is 120 theta, internal, that is 3 MP theta. Okay, theta will be cancelled, so MP equals to 120 by 3, that is 40 kilonewton into meter. Okay, so we have solved the span AB. Now in the span AB, as we have discussed earlier, the moments value was MP. Now in the span BC, okay, moments value is twice MP. Let's keep it in a consideration while solving the term. And now support B as intermediate support, it will act as a fixed support. Okay, so span BC, just a minute. Now say span, just a minute, span BC. Now as we have seen, B is intermediate support and C is, we can say, roller or simple support. Okay, so this is a case of the prop cantilever beam with UDL over the entire span. So for this one, the theoretical criteria is that in this one, plastic hinge will produce at distance of 0.414 L from the prop beam, means prop support. See, this is a prop cantilever beam. Okay, so theoretical criteria suggests that the maximum bending moment will be produced is at the point at the distance of this one. How much? Say from this prop support at 0.414 L. Okay, for example, whole dimensions span is L, like that. So our L is, let me see in the figure, so BC span is 6 meter. Okay, so just a minute. Now as we can see, 0.414 L, point means 0.414 into 6, that will be 2.48 meter. So from the support C, the plastic hinge will be produced at 0.414 L. Total is 6 meter. So 2.48 deducted from 6. So ultimately the remaining one is 3.52 meter. Okay, this one. Now, so this time relation will be different. So let's give the notation, this one as a theta, while this one as a theta 1, and this one, that is theta plus theta 1. Okay, and as twice moment is okay, first of all let's derive the equation between the theta. Say 3.52 into theta, or if I convert it into 3 digit, then it will be 3.516. Okay, so 3.52 times, or we can say 3.516 theta equals to the right hand side, that is 2.48 into theta 1. See, 2.484 into theta 1 equals to this one, 3.516 theta. So I will get the relationship from this one. So theta 1 equals to 1.415 theta. Okay, what I have done, this one into theta equals to this one into theta 1. So I got the relation between theta 1 and theta. Now let's talk about the value of the deflection. So deflection's value can be calculated either left hand side or right hand side triangle. Okay, let's take the left hand side triangle. Like always, we have taken theta. So tan theta equals to, this one is deflection, delta. So tan theta equals to delta, divide by dimension, that is in 3 digit 3.516. So delta equals to 3.516 into theta 1. So tan is very, very small. So this will be the equation, or we can say value of the delta. So I got the delta as well as theta's relation. Now external work done and internal work done. Okay, so first look at the moments. See, as I have discussed earlier also, in the case AB, moment is MP, while in the case BC, moment is twice MP. Okay, so at intermediate point, say B is the support where MP and twice MP both will be acting. So what we need to consider is minimum moment. Say whenever at any support or any point there are two different moments are acting, then always consider the minimum moment. So at point B, I will consider the minimum moment MP, while at the center point I will consider moment that is twice MP. And there is no issue with the C, because as it is a roller support at the end, so moment will not be produced at that point. So in this figure we can see this one at point B, just a minute. See, at point B MP is produced, while at point center point we can say it is twice MP is produced. Okay, while at point C no moment will be produced. Okay, so now let's talk about external and internal work. So talking about external work, formula is load into deflection. Now the load is UDL. So in case of UDL we have already discussed W into L. Say always take the total load into deflection by 2. So W, that is 30 kilonewton per meter, UDL, that is up to 6 meter span, and into deflection by 2 we have already derived the value of the deflection, that is 3.516. let's put down it over here. So I will get, just a minute, let me zoom in. Say UDL 30 into 6 into deflection by 2, say 180 into deflection by 2, so I will get answer, that is 316.44 into theta. Okay, then let's talk about the internal work done. Just a minute. Say in case of the internal work done, first of all this MP into theta, this one, this twice MP into theta plus theta 1, that is this one, and at C no moment is produces. Now we have derived the relation theta 1 equals to 1.415 theta. So let's put down this value of theta 1 as 1.415 theta. Okay, so MP into theta plus twice MP into theta plus theta 1. So let's solve this one. So I will get the answer 5.83 MP into theta. So finally we have got the external work done as well as internal. Let's equal both terms. External work done 316.44 into theta, while internal, that is 5.83 MP into theta. So ultimately solving this one, I will get the value of MP, that is 54.28 kilonewton into meter. Okay, so finally we got the two moments. Span AB's moment was 40 kilonewton into meter, while span BC's moment is 54.28 kilonewton into meter. So final moment will be, as we discussed in the previous example, maximum of the above two moment. So maximum moment will be obviously 54.28 kilonewton into meter. That's the final answer. Now as moment is varying in both spans, say AB and BC, so spans AB's MP's moment is MP. Okay, so that is, we have got the answer, how much? I think 54.28. So see, in case of the plastic moment of the span AB, it is 54.28 kilonewton into meter, while in case of the span BC it is twice MP. So let's multiply the moment with 2. So span BC's moment capacity equals to twice MP. MP is 54.28 multiplied by 2. So ultimately that moment will be 108.56 kilonewton into meter. Okay, so that is the, so see, these are the two examples which we have solved using the kinematic method. Okay.